Hi everyone, let's go ahead and get started with the multi-class sentiment recognition for Twitter tweets using Hugging Face transformers. Lately we have been covering a lot about the transformers and its architecture. We have covered the theoretical part for the BERT and the transformers. We have also covered for the attention networks. If you have missed that, you can visit my YouTube channel, Attention is All You Need, Attention Paper Review. The link of this is given there as well. You can watch it here at my channel KGP Talkie. Alright, so we are just going to recap the transformers and thereafter we will start with the text classification architecture. So in the transformer, as we have been seeing previously, it is a multiple part there. To work with the transformer, like you need to have a data set, you need to then tokenize that data set. Thereafter, you have to use the Hugging Face transformers where you will load the model. Thereafter, you will train the model, then store it and then use it into inference. Thereafter, again, you can use the data set for the testing purpose. We have seen these previously as well when the transformer started, and by this time we are having GPT-4 and GPT-5. Well, so these transformers are a type of the neural network architecture. These things we have already seen that there is the encoder and the decoder. But in BERT neural network, generally we use their only encoder part there. Alright, so we can use this transformer in variety of natural language processing tasks like machine translation, text summarization, question answering, text classification, and so many other things. So this transformer architecture we have again seen previously. I'm just recapping this once again. Here you have your text data. Thereafter the data will be tokenized along with the token embedding and the positional embeddings or positional encoding. Then it will be going here into the encoder stacks, and then finally after this hidden states, this hidden state will be used as the contextual vector here, and then this whole thing will be used as BERT neural network there. Alright, each of these things we have seen previously, but you can see it again here. This tokenized text, this does the tokenization of the input text data. Thereafter token encoding is there, so whatever is tokenized here, then the token encoding happens here. That means those text data gets converted into numerical numbers here or numerical sequences, and then those numerical sequences get converted as the token embedding. Along with that, the position embedding is there as well, and then the token embedding and the positional embedding gets added together. It forms here final embeddings. After this final embedding, then it goes to the encoder stacks. There are multiple encoder depending on what type of a BERT neural network we are using, whether we are using a BERT base or BERT large. In BERT base we have 12 encoders there, encoder stacks, and BERT large have total 24 encoder stacks. Let's go ahead and see how you can use this text classification architecture with the transformers. So in the transformer, you see here you have your token embedding and a token encoding, then embeddings here. Thereafter the encoder stacks are here, and then hidden state. So this whole thing works as the encoder part in the transformer, and thereafter when we are going to use a BERT as the classifier, then at that time this classification head is going to get added after this hidden state. And after this classification head, there will be a loss function like we generally use there, like cross entropy loss function. So that cross entropy loss function will be used to finally fine tune some of the weights of these transformers, so that this can be fine-tuned as the text classifier. So in this lesson we will be using tweets data for our sentiment classification. So here we will be having a multi-class classification. That means we will be having more than 2 classes for the classification. If there are two classes, then it is known as a binary classification, but if it's more than two, then it is known as a multi-class classification. In a one way, binary classifier is also a multi-class classification, but generally that is referred as binary classification. Alright, so this is all about in this lesson. I'll see you in next one. Alright, now let's go ahead and get started with the coding part. In previous lesson, we had seen how you can add classification head over the encoder architecture, and then you will get here BERT classifier. So this is overall encoder architecture for the BERT classifier, and thereafter a classification head is added here. We are going to use a data set here, that is the Twitter multi-class sentiment data set. This data set you can get it at my GitHub repository here. So at my GitHub repository, you need to come here inside this repositories, or you can search this all CSV ML data files, and in this you will find that Twitter data here. So the Twitter multi-class sentiment data. So in this Twitter multi-class sentiment data, you will be having here text and thereafter label and thereafter a label name. So this label is a numerical number 0, 1, 2, 3, 4 and 5, and their label name is actual label here. So that is the alphanumeric, and mostly it is the alpha characters are the word there, you can see. Okay, so I'm just gonna read this directly from the internet, but before that I have imported here pandas as the PD. But before I run this, you need to also make sure that you have installed latest version of the transformers. You have also installed the accelerator, you have installed the data set, you have also installed the BERT visualization, and thereafter you have installed the UMap learn, and then you have upgraded your Seaborn. I have seen that sometimes during the plot, during the matplot, this Seaborn creates a problem where we don't get to see the heat map properly. So by upgrading this Seaborn library, that solves my problem. So here I'm using VS Code Studio. You are free to use the Jupyter Notebook as in separately, or you can use the Google Colab or any other IDE, whatever you prefer. If you are seeing this Hugging Face transformer, so I'm sure you are advanced learner in machine learning, so you must be aware of these IDE. If you are not aware of these IDE, you can visit to my other lectures there. I mean to say that my other courses where I have covered these for the beginners. So that is given in the notebook there itself. You can enroll in these courses and then you can get started as the beginners. Let's go ahead and just run this. So it is going to read this data directly from the internet, and there you can see total 16,000 rows have been fetched from there, and in that we are having text, label and the label name. Let's go ahead and see the info of this so that you can get df.info. You just need to run it. It says that 16,000 non-null data set. That means there is no null value. If you just want to verify that once again, you can just check here df.edge, this should be edge null, and thereafter you can do here sum, and then you can just run it. Then you check there is nothing here, so everything is 0, 0 and 0. So this one is coming from the info, and here this one is coming from df.edgeNull.sum. Thereafter, let's go ahead and check the df.describe. That part you will check here if there is any integer data types or float data type. So for that this describe works. So here it is working only for this label, but moreover it doesn't matter in this case. Let's go ahead and check how many unique labels are there and how many other labels are there. So I mean to say that the value counts there. So there are total 1, 2, 0, 1, 2, 3, 4, 5. So there are total 6 labels here. That means it becomes 6 class classification here. And in these class number 5, or you can say that the class number 6, so this one have the least number of the labels, so it is a little bit imbalanced data set, but it's fine for our purpose. We can work with this without any issues. All right, so this is all about in this lesson. Thanks a lot for watching this. In next lesson we are going to do the dataset analysis. All right, let's go ahead and do the dataset analysis. So in the dataset analysis, I'm just gonna import matplotlib as a pie plot, and thereafter we will start doing the data analysis. So I import here, import matplotlib.pyplot as plt, and thereafter I'm just gonna run this cell, and then I'm going to get the label count. So I write here label counts is equal to df and then label names here. So these label name are the alpha names here. So these are the actual labels or the sentiment written in the word, and thereafter I say here the value counts, and then I say that ascending is true so that it can be shown into the ascending order. All right, so smaller is first and thereafter the largest in the last here. Once you get this, thereafter I'm just gonna do here label counts dot plot dot bar h, that is the bar plot, horizontal bar plot actually. So I just run this. Now you see here horizontal bar plot. Once you have this horizontal bar plot, thereafter I just run it here plt dot title, and in this I say here frequency of classes, and then I say here the plt dot. So I just run this. Now you will see here the frequency of classes. So the joy have maximum numbers and then the sadness, and there is very little surprise here. So during the training or during the inference stage, you might see there your model might get confused with the surprise classes. Do remember this. During the inference we will try to understand this, what impact this have in our model. Let's go ahead and do our the tweets, number of the characters or number of words per tweets, and then we will be seeing it with the box plot. So I write here the df, and then I say here words per tweet is equal to df text dot, in fact I can just do here dot str, and then I can split it. Once split has happened here, then I can just apply here the length function. So apply length function. So once you do that, thereafter you would be able to see there this df word per tweet column is added here, and it says that 4 word for first one, 1, 2, 3 and 4. It's like that only. Once you have this one, then you can just simply write here df dot box plot, and in this box plot you need to say that which one you need as the, you know, which column you need to use as the box plot there for the y-axis. So I say here I want to use here words per tweet as the y-axis, and thereafter I say it here classify it or divide it by the label name. So there would be a multiple you know, the axis, or you can say the multiple divisions on the x-axis for these label name. So I see here anger, fear, joy, love, sadness and the surprise. And the moreover you will see here that average number of words per tweet is a lot higher in the love case as compared to the sadness. So in sadness the average number of words per tweet is lower than the love. Other than that, you will also see here that there are you know, some outliers here as well. So in terms of the outliers, you will see here in case of the sadness you have a lot of tweets which have very lengthy descriptions, or like that you can say here. Okay, so some of the outliers belongs in the sadness classes. Okay, so this is all about in the data analysis. In the next lesson we are going to do the text to token conversion. So our text data will get converted as the token. All right, I'll see you then. All right, let's go ahead and see how these text data can be converted as a token, and thereafter how these token gets converted as the embedding later on. So any transformer model cannot receive raw string data as the input. Instead, they assume these text data is tokenized and it is encoded as the numerical vectors. And all these things happen in the tokenization steps here. So the first of all, I'm going to import auto tokenizer from the transformers, and thereafter we will be using model checkpoint BERT base, and then we will do the tokenization. So I write here from transformers import auto tokenizer. All right, so this you can check it here that auto tokenizer and Hugging Face, these are the auto classes. So in these auto classes we have the auto tokenizer. So why this auto tokenizer is very helpful? Because it automatically identify the model based on the it automatically fetch the correct tokenization based on the model checkpoint. So I'm just gonna assign here the model checkpoint BERT base. So I write here model underscore CKPT is equal to BERT hyphen base hyphen uncased. So uncased says that it is irrespective of the case, that's mean lowercase and uppercase, all these are considered as a single type of the text data. Thereafter I write here the tokenizer is equal to auto tokenizer dot from pre-trained, and thereafter I write here model checkpoint. I just run this and then I check it here. It has successfully imported the tokenizer from the Hugging Face. Now you can use this for text tokenization. Just to test this tokenizer, I'm just gonna take here the text data. So I define here, text is equal to, I say here, I love machine learning, and then I say here tokenization is awesome. Okay, thereafter I write here encoded text is equal to tokenizer, and in this I pass this text data. Thereafter I'm just gonna print this encoded text data. So I just run this. Then what do I see here? I see input IDs, I see token IDs and attention mask. If you remember in our previous section where I was covering BERT models, BERT transformers, at that time I told you that it outputs actually 3 keys: input IDs, token type IDs, and then we have the attention mask. So this attention mask says that while forwarding these for the embedding and for calculation of the embedding, in fact, then if attention mask is 1, that means all these will be used for the calculation. And token type ID says that which type of sentence is this. If you remember, in BERT models we have 2 sentences generally, sentence A and sentence B. So that is why that next sentence prediction, that is the NSP, that happens there. But in text classification task, we pass just single sentence, and based on that single sentence, that CLS token generates the embeddings there, so we get the output. Okay, so this CLS actually, this one is used as just a single sentence A. Sentence B is not present here. If multiple sentence is used there for next sentence prediction, then you will be having 2 type of the token type IDs here, 1 and 0 there. Alright, so this is the encoded text. That's how these encoding happens here. Let's go ahead and check the vocabulary size here. So I write here tokenizer dot vocab. So I just write here tokenizer.vocab. So here I check all these vocabularies so which are used there, and length of this you can simply check, like length of tokenizer.vocab. This says that 30,522. So this is total number of the tokens available in BERT model. Other than this, you can just simply check here that with tokenizer.vocab size here, and the maximum length you can also check here, that how much maximum token it can take there. So it says that 512 max token length is here, and total number of tokenizer available here, that's mean total number of dictionary available in this tokenizer is 30,522. Alright, so this is all about in this lesson. I'll see you in next one. Hi everyone, let's go ahead and get started with the data loader and train test split. So in this, I'm just going to first load the data set, and in this I'll be loading data set directly from the data frame. So you know the transformer doesn't work directly from the data frame, so we have to load this data frame as the data set and data set dictionary so that it can be compatible with the transformers in Hugging Face, and thereafter we can build our model. So first of all, we have to call train test split so that we can split this data as a train test split. So for that we have to call that train test split from the sklearn. In fact, I think the train test split I might have called, and but doesn't seems like I have that, so I need to call here from sklearn dot model selection import train test split. Once you have this, then I say here the train and test data, then I say here train test split, and in this I just simply pass my data frame, and thereafter I say here the test size, I'm going to use 0.3. So basically this training data set is going to have the 70% of the data. If you check this data frame, train data frame is here. So this one is going to have this 70% of the data, and this one is going to have the 30% of the data. Other than that, I'm just going to also stratify it. So I write here stratify, and the stratify label, I'm just gonna put it here, stratify is label name here. Okay, seems like it won't work there directly, so I can just simply put here stratify as df label name. Let me see if it works perfectly. So it has worked here. So I have got now the train. Now I'm going to split this test with the validation and test set once again. So I write here test and then validation set. So once again I write here train test split. This whole thing I'm just going to copy from here, and then I'm just gonna put it here. So now instead of this df, I'm going to put here the test, because I'm going to get it from the test samples. So this test sample is already 30%. Now this validation I want 10%, so I write here 1 divided by 3. That means the 10% will come in validation and 20% from this original data will come into the test set. Okay, so I have got this. Now I can simply write here, in fact, I'm sorry, train.sep, and then I can write here the test.sep, and then I can write here validation.sep. I just run this. Seems like something is wrong. Let me just check it here. What happened here? Inconsistent number of samples. Yep, here the samples are different. So test. Okay, so now it's fine. So you check that 11,200 is going to be the train set, and rest is going to be the test and validation set. Now we need to import data set and data set dictionary from the data sets. So from data sets import data set and data set dict. Once you have that, then you can simply start building your data set. So I write here dataset is equal to dataset dict. Inside this dataset dictionary, I need to first build my train set. So in this train set, I write here train. A dictionary, in fact, I need to create here. A 3 dictionary I need to create. 3 keys in this dictionary, in fact, I need to create. So then I'll be having here the test set, and thereafter I'll be having here validation set. In these, I need to again put here the data set dot load from. You can simply write here dataset dot from pandas. Okay, and in this I write here my train samples. Okay, this one is complete, and then simply I just copy it from there and I paste it here and I say it as a test sample, and thereafter for this validation I copy and paste it here and then I say it for validation sample. Okay, thereafter you have your data. You can just simply run this. Now you will be having your data set here. So in this data set you are getting text, label, label name, and word per tweet, which we already had previously, and here this one. So this one I think is coming. If I can ignore something, ignore index or like that, let me just check it. I'll get back to you. Yeah, so I got that. That is actually preserve index need to be false. So I just need to make sure that I do not need to preserve the index, so it won't display this one. Perfect. I just run this. Now I have here text, label, and label name. So this is a perfect format which we actually need for our model. So this is all about in this lesson. Thanks a lot for watching this. I'll see you in next one. Alright, let's go ahead and see how we can tokenize our emotion or sentiment data which we have downloaded from a GitHub repository, Twitter tweets. So for the tokenization of our data, we need to again visit our data set and see how many columns are there. So these are the columns available in the data set. Like we have a train, test, and split, train, test, and validation splits, and these are the number of rows available here, and these are number of columns for each of these splits here. You can traverse through these train data, test data, or validation data. Thereafter you can put the index which you want to see. So I want to see here the first data that it says I feel I'm being generous with this statement, and then label H2. So do remember that this thing what you see here, that this label is a default column name requirement for the target variable, and then this text data we will be passing for the tokenization. So after the tokenization, like we had seen previously sometimes back, we saw their input IDs, token type IDs, and attention masks. So these will be returned from the tokenizer. So let's go ahead and write here a sort function. So that I write here def tokenize, and then I write here the batch. So I'll be using map function as well. So I write here the temp is equal to tokenizer, and in this tokenizer I pass here the batch text data, and in this text data I say here the padding is true, and thereafter I say the truncation is also true. So when the truncation is true, that means whenever it goes above the maximum length, it will automatically truncate the data and then return here temp. You can also provide here the max length as well. As of now, I'm gonna provide it 512, or you can just leave it as a blank, so it will automatically take the maximum length of your overall data set. So I return here the temp, and thereafter I'm just gonna get here print, and then I'm just gonna pass this one just to see that how this tokenization is going to happen. So as soon as I pass this, I'm sorry, I need to also call here tokenize. Okay, so inside that I pass this, and now I see there you have got input IDs, then you have got token IDs and attention mask. So this is what returned from this tokenize. Let's go ahead and see the first two variables, first two rows actually for the tokenization. Now what you see here in the first one, now you can clearly see that after this 102, which is the separator token, then we are seeing here these are filled with the 0. The reason is here the second one, what we see here that have a quite high length here. Alright, so the lengthwise it is quite large. That is why this was becoming smaller than the second one. So the rest of other got filled with 0. That you can verify with like this 0 and then 1. Now you will see here one have a larger text data as compared to this one. So that is why you see that kind of behavior there. Let's go ahead and write here emotion underscore encoded is equal to dataset dot map. So I use here a map function to tokenize our data. Thereafter I say here batched is equal to true, but the batch size I'm just gonna set here none. So whenever I set batch size is none, that means whole data will be passed as it is without any batch size. So I'm just gonna run this. Now it's going to run it, and then you will see this encoded, emotion encoded have these additional columns here: input IDs, token type IDs, and attention mask. Alright, so we have got our data encoding. Now we need to find out label to IDs and ID to label. So these are the two important variable which we will be using later on, label to ID and ID to label. So these are like you see these labels, what you see there, these are the label. So label actually in Hugging Face, so these alpha words are known as the label, and these are the IDs here. So there is mapping. We have to create a mapping between these label name and labels, so which will be known as label to ID and ID to label. So that having said that, I'm gonna create here label to ID equal to for x in dataset train. Alright, so I'm just gonna iterate over the train sample, and once you iterate over the train sample, I'm going to get label name from here. So I write here x label name, and corresponding to that I'm just gonna put here x label. So that I create for the label to ID, and then I create for ID to label something like this. So here I write for key and value in label to ID dot items, and once you get this, now we need to just inter-exchange these together. So this will be coming now as a key, and this will be going as the value. That means here value becomes key and key becomes value. Alright, so this is the label to ID. Let's go ahead and check this. So here you have got label to ID, love, joy, sadness, fear, anger, and surprise. And similarly you have got ID to label. So there 2 corresponds to love, 1 corresponds to joy, 0 corresponds to sadness. Alright, and so on. Perfect. So this is all about in this lesson. Thanks a lot for watching this. I'll see you in next one. Alright. So the tokenization has happened for all the data. Now we are going to build the model. So for the model building, I'm gonna load the auto model. In fact, I'm going to first import the auto model. Thereafter, I'm going to load my model through the auto model. So I write here from transformers and then import auto model. Okay, perfect. Thereafter, I write here import torch and then I just run this. Thereafter, if you remember that our model CKPT is BERT base uncased, so I just call here model is equal to auto model dot from pre-trained, and then I just call here model CKPT, that is the model checkpoint. Okay, so this auto model is going to load here BERT base uncased model. Okay, I just run this. Thereafter, I can just simply copy this model and print it here. So first of all, it's going to download this model weight from the internet. So it will take a while. Okay, so the model weights are downloaded. Let's go ahead and run this model. So once I run this model, you see here the details that it is a BERT model. It has here word embedding. So the first of all word embedding is done here. That is the first layer. Thereafter the positional embedding is done. Thereafter the token type embedding is done. And then the layer normalization is done. And then finally the dropout is here. So this whole thing is as a BERT embedding. So this with the help of this you can recall our this example where we saw there these kind of encodings and embeddings were happening before these data going into the encoder stack. So the same thing is happening here in this model. So all kind of embedding is happening here, and thereafter it is going into the encoder stack. How many encoders are there? There are 12 encoders. So it says that it is the module list, and in this module there are 12 encoders there. All right, so these stacked are there. So it starts with the attention networks, thereafter the output layer, and some of the intermediate layers are there. You can see it here in the more detail. So in this you see, first of all, in attention network a query layer is there, and then the key layer is there, and then the value layer is there, and then finally some dropout happens here. After this query key and value layer, then all these goes there as a data, then the normalization happens, addition happens, then again another dropout happens here. Thereafter it again goes through the linear transformation. Once all these things happens, and then at the target output once again it goes through the linear transformation. Do remember, till now there is no classification head. So no classification head is added till now. That classification head we will add later on. You can also go through with this model in a little bit more detail, like you can call the config. Thereafter you can call other parameters like architecture. So architecture is BERT for masked language modeling. So this one. So there are two type of BERT language modeling is there. BERT for masked language modeling and BERT for next sentence predictions. You can also check more parameters with this, like you can check like this BERT word IDs. Okay, and so many other things probably you can check. Currently don't have anything BERT word IDs. Other than this, you can also check here like model state probably. Let me just check it here. Okay, do we have anything? Okay, config dot, I'm not sure what are other things, like you can check it here, but there are obviously so many things which you can get from this, like ID to label probably. So currently we don't have any. By default it is initialized as binary classifier, but yeah, later on we will be initializing it with the all set of ID to labels and label to ID. So this is the same thing what we did earlier. So once we pass this during our model initialization, then it will be having all these stuffs there automatically. Just in case if you want to see everything, then you can just simply print here the model.config. So it will just print everything. So this is overall configuration of the model here. So it says that architecture is here, but for masked LM and so many other things here it has, like the total vocabulary size here 30,522, and then it is using cache system. So basically if its weight is already downloaded, so do not download it from the Hugging Face, that's all. Hidden dropout probability is here 0.1. Attention dropout probability is also 0.1. Intermediate size is here 3072. So intermediate layer, you can say there the embedding size internally in intermediate is state, overall size is 3072, but the final size is 768. That is the hidden size here. You also see here the max position encoding, so it says that 512. So this position encoding limits our context vector size, or you can say there the number of tokens there. So that is why in BERT the total context tokens are limited to 512 only. So this input token size is 512, but the embedding size which gets generated at the output, that is the 768. All right, so this is all about in this lesson. I'll see you in next one. All right, so we have reached to the final stage of our model building. Now we are going to import model and we are going to prepare our model so that we can do the fine tuning of the transformer. Just to recap, now you know that how to convert our text data into the token embeddings, and thereafter how you can apply these encoder stacks. So we have already seen that in a BERT model how all these encoder stacks are combined together, and then finally these classification head will be added, and thereafter this whole data will be passed, and then the fine tuning will be happening to this whole model. So we will be using here auto model for sequence classification, so that we can add here classification head. After adding these classification head, cross entropy function will be used as a loss function there. All right, so this method will automatically add this classification head in your model. So we will be using this one instead of the auto model. Let's go ahead and import these from the transformer. So I write here from transformers import auto model for sequence classification, and thereafter I also need to download here, I need to also import here auto config here. So once you have all these, then I say that how many labels are there. If you remember, by default our auto model had 2 labels only, that was the binary classification, but here I'm going to define that how many labels need to be there. So I say here label to ID, this should be 6 there, so there are total 6 labels, and thereafter I need to also tell that where I want to train my model, whether on CPU or GPU. So I have a GPU, so it will be trained on GPU itself, but if you don't have, you can train it on CPU, but definitely it is going to take a lot of the time. Then I'm going to get their GPU or CPU device automatically, so that later on when we do the inference or any other things, so whatever is available on our PC, it should be able to use those automatically. So I write here torch dot device, and in this I say that use CUDA if torch dot CUDA dot is available. So if CUDA is available, then use CUDA, else use CPU. Okay, so we have got here CUDA and CPU, and then I write here config is equal to auto config, dot from pre-trained, okay, and thereafter I write here model checkpoint, that is the model CKPT, and then I write here label to ID is equal to label to ID, and I also write here ID to label is equal to ID to label. So why these two part is important here? So these two parameter is important because once we save our model, so we need these configuration in the model itself, right? So you don't need to store these label to ID and ID to label during the prediction. So it will automatically convert your prediction into readable label format instead of printing some prediction IDs there. Thereafter I write here model is equal to auto model for sequence classification dot from pre-trained, and in this I write here model checkpoint, and then I also write here config is equal to config, which we have just defined here, and thereafter I move this model to device. So what is this device? This device you can check it here. This device should be CUDA because I have a GPU here. So our model will be trained on the GPU. So this warning you can ignore. So why this warning is coming? You know, this model is initialized with the default weight of the classifier classifier head here. So these classifier head get initialized with the random weights. That is why it is saying that these classifier head got initialized with some random weight. If you intend to use this whole model as a classifier, then you have to do here a fine tuning. Otherwise you might not get a good accuracy. Let's go ahead and compare this model what we had seen earlier. So I just print this model here, and then I go in text editor. Everything seems as it is like we had seen previously. We have here initial BERT embedding layers, and thereafter we have encoder stacks. 12 encoder stacks are there. We have here BERT pooler as it is like we had seen previously, and thereafter we are having here a classifier head. So this thing we did not had with the output feature as 6. So we have defined this out feature equal to 6 this time. So this is going to be used automatically as a classifier head with the 6 output, and in final softmax activation function will be automatically used there. If number of features are more than 2, then the softmax activation function gets automatically used. Otherwise sigmoid activation function is used there. Okay, so that's how you can also print model.config. So with the model.config you would be able to see all these things in the detail there. So these are the ID to label. If you remember, these were not available previously. If you see it here, so ID to label or label to ID, these were not available, but here it is available because we have initialized this. So that is why we need these label to ID and ID to label, so that when we use our model in the production, we don't need to maintain these label to ID and ID to label list separately. So it will automatically use these from the model itself for the prediction, and rest of other things are same as it is what we had seen previously. Alright, so that is how you load your model. In the next lesson I'll show you how you can build your training arguments, and thereafter we will move forward for the training. Alright, I'll see you then. Alright, let's go ahead and get started with the training arguments. So first of all, you need to import training arguments from the transformers. So I write here from transformers import training arguments. Okay, so once you have a training argument, then you can start building your training argument. So first of all, we need to define here the batch size. So I define here batch size is equal to 64. Thereafter you also need to say that where the training will happen. So I write here training underscore dir. So this will be the training directory. I say here BERT underscore base, and then I say here train underscore dir. So this is going to be the training dir. Okay, thereafter I need to build the training argument. So there I say training args is equal to training argument. So in this training argument, you will see there are so many parameters in this. You just copy this thing from here and paste it here. You will see a lot of things in this training argument. So you need to go here in the trainer, and inside this trainer, you will see there the trainer and the training arguments. I just need to find out there. Yeah, here it is. So there are so many parameters like output dir, where our model training will be stored, and thereafter it says that overwrite output dir, by default it is false, we will be making it true, and so many other things. Let's go ahead and see what are important for us, and we will be using only those here. So the first of all, I say here output dir is equal to training dir. Thereafter I say as overwrite. Let me see, where is that? It doesn't seems like there. I'm just going to get it here. Overwrite output dir. I say it here, overwrite output dir is equal to true, and thereafter I write here another one that is says that the number of train epochs, and that part I'm going to do as 2, so it is going to train for 2 epochs, and thereafter I say here learning rate. So learning rate I say here 2 e power minus 5. Okay, thereafter I say here per device train batch size, and that part I'm going to say here equal to the batch size, and thereafter I say here per device eval batch size is equal to batch size. Thereafter I say here weight underscore dk is equal to 0.01. Then I say here evaluation strategy. Okay, then I say here that as the epoch, and then I say here disable underscore tqdm is equal to false. That's all you need to do here. So we have got our training argument. Perfect. So it has run here successfully. Once you get the training argument, thereafter you need to build here a compute metric. So why we need these compute metrics? You know, for evaluation of your model, just to evaluate your model, you need their compute matrices. By default, Hugging Face does not have those compute matrices inbuilt. You have to make your own compute matrix so that you can identify that how much accuracy your model is getting during the training and evaluation page. So that compute matrix we also need to build that. You can search that compute matrix. I'm not sure if that part is available here. Let's go ahead and just search it here. Compute matrix. Okay, so in the text classification task here, they have predefined compute matrix here. So similar to this, we will be building our compute matrix as well. So what we will do here, we will say here compute matrix eval pred, then we will be doing here like this, where predictions labels eval predictions, and then we will be doing something like this. So either you can import these evaluate and then load this accuracy from here, or you can use this compute matrix by default directly from the sklearn as well. So it depends on you which one you are going to use. Alright, I'll see you in next one. Alright, so let's go ahead and get started with building our compute metrics so that we can evaluate our model properly. So we are having here two options to build our compute matrix. One option we already have here. So for this one, I'm going to use this evaluate library. You just click on here. You will come to at this place, and then you can just click on tutorial. So it says that you need to install this evaluate. So I am sure I have already installed this, so I don't need to install it once again, but I'm just putting here for your reference. Okay. So the first of all, you need to install this evaluate. Once that part is done, then I'm just going to copy this whole thing from here. So I just copy this from here, and then I paste that here, and after that I again copy this whole thing from here, and then I just put it here, and then this numpy I put it here. So import evaluate, import numpy as np, and thereafter evaluate.load accuracy metric is here, eval pred comes here, and then here compute metrics, and then finally it returns accuracy. Okay, so this is one way to build your compute metrics using evaluate. Other than this, you can use default sklearn matrices, to build your compute metrics. Okay, so here I write from sklearn dot metrics import accuracy score f1 score. Thereafter you write here def compute metrics. Okay, so this one I'm just going to put compute metrics evaluate, so that I'm sure that it is using evaluate function, evaluate library. So it's working now. Def compute metrics. So default def compute metrics will use sklearn matrix, and inside this it accept parameter pred. So these pred parameter automatically passed during the training, so you don't need to call all these separately. You just need to put this compute metrics in the trainer. It will automatically pass this pred here, and then this pred will be having predictions and the labels together. Thereafter I say here labels is equal to pred dot label underscore idg, and preds is equal to pred dot predictions dot argmax, that is the argument max. I need to get it here -1. So you see here I got labels and thereafter predictions from the eval pred directly. Okay, and then these predictions got modified with the np.orgmax. So basically these things are same what we see here. So this is almost exactly the same what we are seeing there. Thereafter we need to get here the f1 score and then accuracy. So I write here f1 is equal to f1 score, and inside this I pass this labels is equal to labels, and thereafter I pass here pred, this one I pass this one, that is the preds, and thereafter you see this is y true and here y pred. So these two things I have passed here, and the average by default it selects something, but yeah, I'm just going to select average as weighted. Alright, so average is weighted here, and then I select here accuracy is equal to accuracy. So this accuracy score I'm just gonna get that from there. Accuracy score, again I pass here labels, that is the y true, and then here preds, that is the predicted value, y pred. Okay, once all these things are done, and then I write here return accuracy. So I return accuracy, and then also I return here F1 score. So I return F1 score as F1. That's all I need to do here. So this spread seems like, yeah, it is here and here. Okay, this I need to remove. Otherwise, if I pass here the parameter name, then I have to pass the parameter name for this one as well, because I have passed the parameter name here. Okay, I just run this. So our compute metrics are ready now. Okay, so these are the multiple ways which you can use to build your compute metrics. Thereafter you can use any of these methods during the training. All right, I'll see you next lesson where we will start building our trainer. All right, so our compute metric is ready. Now let's go ahead and start building our model. So I say here model and trainer actually. So the model building has already happened. I just need to build here the trainer. So once everything is done, then I can import the trainer from the transformers. So I write here from transformers import trainer. So trainer starts with the capital T there. Thereafter I write here the trainer is equal to trainer, and in this I need to pass first of all the model which I'm going to use. So it is the BERT base model, BERT base uncased model. Thereafter I need to pass here the training argument. So I write here the argument is equal to the training arguments. Thereafter I need to pass here the compute metrics. So I'm just going to pass here the compute metrics which I built from the sklearn. Later on you can also try on passing compute metrics which you have built from the evaluate library. Anyone will work fine. Okay, thereafter I write here the train dataset. Okay, so train dataset is equal to, I already have this emotion encoded, and in that I'm going to pass their train. So if you just run this, you will see here, okay, let me just remove this as well. So I have here this train split. In this train split there are multiple columns. We do not define any column in the train data set. So how the model will know that which column it need to use? By default, model will use input IDs and labels there. So these will be directly used as the input and output. So this will be used as the input, and there it will be used as the output, and rest of other things will just get discarded. In fact, this will be also used there, and this one will be also used. So all these will be used there by default. So do not change these names during your data preparation. Okay, thereafter I say here eval dataset is equal to emotion encoded, and then in this I pass here validation split, and thereafter I also need to pass here the tokenizer. So tokenizer I need to pass as it is. So this is the tokenizer which I had loaded initially when we started this section. So this is the BERT base uncased tokenizer. These are some of the special tokens used in the BERT base tokenizer. If you remember that, you might have seen that any sentence start with the 101 ID, that is the CLS token, and then it ends with the 102, that is the separator token. There are some other tokens like 0 as the padding token, 100 as unknown token, and 103 as a mask token. So this is the tokenizer which we will be using. I'm just gonna run this trainer from there. Now we have reached at the stage where we can start our model training. So you just need to do here trainer.train. So it is going to train for 3 epoch which we have given into our trainer arguments here. So in fact it is just 2 epoch, not the 3 epoch. So for the 2 epoch it will train, and then it will use compute metrics as this one where it will print accuracy and F1 score, and here the training has started. So it's going to take some time for the training. Okay, seems like it is going to take around 30 to 40 minutes to finish this training. So we have to wait for that much of the time. Given the constraint on your GPU, it depends that how much time your model is going to take for the training. Okay, seems like it has increased, but I'm sure it won't take this much of the time for the training. So it will decrease these training time as we move forward. But as of now, we can wait this much of time to finish this training. If you are using Google Colab, this training should be faster. If you are using other GPU other than mine or any faster GPU, your training should be fine. Your training should be finishing in like 5 to 10 minutes only. It shouldn't be taking this much of time. Okay, so this is all about in this lesson. I'll see you in next one. Alright, so the trainer has finished the training. Now you can clearly see here, in first epoch, evaluation accuracy was 85%, but in second epoch, evaluation accuracy has gone above 90%, which seems quite good on given that we have trained it only for 2 epoch. If we keep increasing these number of epochs, we might get better and better accuracy. You can also play with other hyperparameters like learning rate, batch size, just to see that if this training accuracy increases there. Alright. So this is the final, the log which got printed. Initially it said that it will take around 40 minutes, but finally it finished the training in 22 minutes on my GPU. Okay, so all these things have happened. Let's go ahead and do the evaluation, model evaluation. So I'm just gonna write here that model evaluation. So once the training has happened, then you need to do the prediction on the test set. So I'm just gonna write here the preds output is equal to trainer dot predict, and in this I say that emotion encoded test set. So this test on the test set, these prediction will happen and that will get stored in this preds output. And then in this preds output, you can just simply write here the metrics. You just run it. Now you should be able to see the final accuracy, the printed in preds output dot metrics. Okay, so on test set we are getting here a good accuracy as well. So around 90% of the accuracy on the test set as well. Let's say if you want to print the classification report and then finally the confusion matrix, then how would you do that? So we have here preds output dot predictions. So these predictions are given as the logits here. So these are the logits in the softmax. If you apply the softmax in this, then you will also get the probability. But probability we don't need. We need that which index there. So label ID actually, which index have a highest logit. So whichever have a highest logit, that will be having highest probability. So we are going to get the argmax from this predicted output. So that will be treated as ypred. So I write here y underscore pred is equal to np dot argmax, that is the maximum argument, and in this I say that axis is equal to 1. So now if you check your ypred, it will be like this. So this is the predicted IDs. Now we already have ytrue. So ytrue you can get from the test dataset as emotion encoded from the test set. You need to get all rows in the test set, and from there I need to get the labels there. Alright, so these labels are printed as IDs there. If you just want to verify this, you can just run this one. Instead doing that one, you just run it here, the 0th one. So you see this label is having here IDs here. So that ID is coming here, that is as a ytrue. So we have got ypred and ytrue. Once you have got all these, then you can import the classification report from the sklearn. So you can write from sklearn dot metrics import classification report, and in this classification report you can simply run this classification report. In that you will pass ytrue and then y pred you will also pass here. Okay, let's go ahead and run this. You will see here that overall accuracy 90% here, and seems like F1 score and accuracy is a little less for the target ID 5. So which one is this? You can just print here label to ID just to check that the 5 one is the surprise. If you remember, we had talked about this initially, that surprise have a least number of the rows, so there was possibility that this might not do a better better classification, or this might not perform better, and seems like that is true here. So this one surprise is actually creating overall issue, and this is bringing down accuracy, overall accuracy. And other than that, we also see there the love is also a case here. So this love one seems like also creating a problem. So this love and the surprise. So in these two things, there are extreme emotion, either in surprise and love, and seems like while representing these extreme emotion, our model is suffering. So what you can do to handle this, you can increase the number of samples in the surprise rows, and you can also increase the number of samples in the love rows. So you might ask that we don't have much samples, so what to do with this? So if we talk in the perspective of production environment where you work in the industry, so there you always have an option to increase your data set. Okay, so that option is actually quite costly, so you need to get involved with the manual annotation, or you get it annotated by someone else. So it's like that. If you are working on any project in production in your company and you see that some labels are creating a problem, just to handle that thing, what you can do there, you can increase the number of samples for that label, or you can balance your overall data set and just see that if your accuracy is getting increased. So these are some of the tips to increase the accuracy. In the next lesson, I'll show you how you can plot the confusion matrix. All right, I'll see you then. All right, let's go ahead and do the confusion matrix plot. So here I import cborn as SNS, and thereafter from sklearn.metrics I import here confusion matrix here. Thereafter I write here import matplotlib.pyplot as plt. All right, so I have imported all the necessary libraries which is needed for the confusion matrix. Now I need to get here the CM, that is the confusion matrix. So I write here confusion matrix y true comma y pred. Okay, so once you have this one, then you can just simply print your confusion matrix. You will be seeing it something like this, and in this you will always see that on y-axis you have actual values, and on the x-axis you have the predicted values. So currently we don't have labels here as well, so we need to print the labels on x-axis and y-axis as well. So I write here the plt dot figure, and in this I need to write here the fig size, that is the figure size 5 cross 5, 5,5 you can say, and then you say SNS dot heat map, that is the CM confusion matrix, and then you say that anote is equal to the true, and then I say here x tick label, that means these will be their label to IDs dot keys, that is actually the labels, and thereafter I say y tick label is equal to label to IDs again is keys. Once you have all these, you can just simply run this to print our heat map. We see it something like this, not very good. We just need to do a little bit more formatting here. So I write here the format fmt, and that format I'm going to see that as an integer. So I say as print it as an integer. Now I see it here like this. Thereafter I need to remove this color bar as well. So I say that C bar is equal to false, and thereafter I just run this. You can also change this color map as well using C map. In this C map, I'm gonna just say here reds here. Okay. So it is something like this. So what we see here, I see surprise have, this surprise have wrong classification in anger and joy, and seems like it could be logical here because surprise is extreme emotion here, and sometimes you can relate surprise with the anger as well. So seems like that is why your model is giving you less accuracy for the surprise rows or surprise labels. Along with that, you can also say that surprise is joy. When joy happens at extreme level, then that gets converted or surprise, or when joy starts happening just before that, when you get the information for the joy, so that moment is also a kind of surprise. So that is why we are seeing these things. We also saw a little bit misclassification in the sadness as well. So in the sadness, you see this sadness got misclassified with the joy as well. Okay, so sometimes it's not clear that whether it is joy or sadness. Okay, it's like, let's say I'm talking about life, and I talk so much about the life, and then finally write there, yeah, live happy life or enjoy the life. So seems like the person is talking about the joy or sadness, so there the model might get confused. So it is like that what is happening here. Thereafter, I'm just going to do here the plt dot y label, and then I say here the actual, and then plt dot x label, and here I say as predicted, and then I say here plt dot so, and then I just run this. So here I have got actual one, and there I have got the predicted one. All right, perfect. So this is all about in this lesson. Thanks a lot for watching this. I'll see you in next one. All right, let's go ahead and build the prediction function and store our model so that you can use it for the later purpose. So I'm just gonna write my text data so that we can start doing the prediction. So I say that I'm super happy today. I got it done finally. So let's say this is my text data and I want to do the prediction on this. What type of emotion is this? So first of all, I need to get here encoding of this text data. So for that, I say that input encode, right, is equal to tokenizer. And in this, I pass this text data, and then I say that return tensor is pt, that means the PyTorch tensor will be returned, and then I want to store it onto a GPU because our model is already stored on GPU. So if we store it on same device, it will work, otherwise it will throw the error. So I just run this. Now I see that this text got converted as input IDs. So our model need these input IDs for the prediction. So now I write here with torch dot no grad. That means I'm just going to do the prediction without any gradient. So overall prediction will be fast here. I say here outputs is equal to model, and in that I need to pass the address where this input encoded is stored. So I write here outputs is equal to model input encoded. Thereafter I just run this, and then I get here logits is equal to outputs dot logits here. Okay, so I just run this, what I see here in the logits part, if I just I just print it, I'm getting here logits. So you see the maximum value, this is not the probability, do remember that, this is logits, you need to apply the softmax here to get the probability. So this maximum value represents that the index at which you can get your, index which is representing your emotion actually. So here you can use, the maximum argument to get the prediction. So I write here pred is equal to torch or np.argmax, whatever you prefer, you can use anything. So I write here logits, and then the dimension is 1, that's mean along the dimension 1, and then I say here item. Then I get here pred, it says that 1, and that index, that is the index, and actual label you can get from id to label, and then you write here pred. So you get that it is a joy, and it is definitely a joy. So that is how you can build your classification method. You can print it here. Let's go ahead and put all these together in a function. So I'm just going to copy this whole thing from here, or I can just make here function like this, get prediction, and in that I pass this text data, and then finally I can return this. All right, so something like that you can return from here, or I can just remove this pred and I can directly return id to label, and then I can call here get prediction, and in that you can just pass your text data. So it says that it is a joy. So that is how you can build your prediction function. Let's go ahead and see how you can store your model. Model storage is quite simple. You just need to call your trainer, and thereafter you need to say that save model, and thereafter you need to give the name of the model. So I say here BERT base uncased, and thereafter I say here as sentiment, and then model. Okay, I just run this, it will save this BERT base uncased sentiment model. Now you see there is no directly something like this. Here this was the train dir. I'm just gonna run this. Now you should be able to see here BERT base uncased sentiment. In this you have got the configuration file. So this is same configuration file what we had seen earlier. It has id to label and label to IDs, and here model dot tensor safe tensor, this is the model weight, and here are the special tokens, these are the tokenization configuration, and here is the tokenizer. So it has all the dictionary libraries here in the tokenizer. You can see all these things written there. Okay, everything you can get it here. Okay, the model.vocab, so this is whole vocabulary, and here is the vocabulary.text. So these kind of the vocabularies are used. The total numbers, if you count, 30,522 as we have seen earlier. Okay, so once your model is stored here, now you can directly call the pipeline method to load this model. So you don't need to do all of these things. In fact, if you have stored your model, you can directly use the pipeline for the prediction. Use pipeline for prediction. Earlier I had shown you a raw method to get the prediction, but you can also use the pipeline method to get the prediction. It is quite simple and straightforward. From transformers, import pipeline, and then simply you can say that here classifier is equal to pipeline, and in that you write here text classification, and then you pass here model is equal to BERT base uncased sentiment model. So this is from where model is going to be loaded, and then you have here the text classification. So this will be loaded as the text classifier. Thereafter here you have the classifier, and in this you just need to pass your text data. So I just pass here my text data. So it's going to do the classification. It says that it is a joy, and here it says that the accuracy. You can also pass here the multiple the text data as well together. So you can pass here a list as well for the classification. That list you can pass here as well without any issue. So I have here label, joy, and score. Let's go ahead and pass more data. So I say here, hello, how are you? Then you will be getting here the two outputs. So both of these are joy. Thereafter I say here love you, and then I run it. I get here a love with the 64%. Thereafter I write here I am feeling low, and then I just run it. Thereafter I say here it is a sadness and 97% of the accuracy. Now you can decide that which method you want to use. This is quite simple and straightforward, and this one have lowest number of the code, lowest number of lines in your code. This one is the raw method. It gives you the more control how you want to do the calculation and other things. So it depends on you which one you want to utilize. All right, this is all about in this lesson. I'll see you in next one. All right, so let's go ahead and build a Streamlit application so that you can use your model with a user interface where you can pass the text data, and that will be giving you final predicted labels. So I'm just going to create app.py file here, and in this file I'll be doing import Streamlit as st. If you are a beginner to Streamlit, you can visit to my channel at KGP Talkie. So at the KGP Talkie, in this playlist section, you will be having here Streamlit tutorial for the beginner, and in this Streamlit tutorial you will be having here a complete Streamlit tutorial. So I'm just gonna copy this whole thing from here, and then I'm just gonna paste it here so that later on if you want to visit my YouTube channel to see this full list of Streamlit tutorial, you can visit there. So I import here, import Streamlit as st, and thereafter import pandas as pd, and thereafter import numpy as np. Once all these things has happened, started with basics of okay, I just need to stop this. Started saying something there. Okay, so import numpy as np. So once all these things have happened here, import numpy. Thereafter I say here from transformers import pipeline like we did earlier. It's pretty much simple. And then I say here st dot title. I'm just gonna give the title for my application. So I say here fine tuning BERT for sentiment multi class, for, in fact you can say there Twitter tweets for multi-class sentiment classification. That is how it is going to run. Let's go ahead and open it into our integrated terminal. Once I open this, I now just need to run this. So I write here Streamlit run app.py. You need to make sure that your file which you are running in a Streamlit, that need to be in the directory where you are here. So you just need to run this. It's going to run it. All right, thereafter you will be having here URL which you can use to access your Streamlit application. And I should tell you, in between I had to stop video, so I restarted it again. Okay, there is no change in the code. Everything is as it is, so you don't need to worry about that. So I'm just going to copy this link from here, and then I'm going to paste it here. So in fact, I already have that here, but let me just show you here again. So once you paste it here, you should be able to see your Streamlit application. One more thing here, if you run your application, you should be able to see this URL automatically. Currently, I'm just copying and pasting it there, but by default, you should be able to see that page automatically. Once you run Streamlit run app.py, it will open that particular page automatically. So now you have your application here. This is the title in your Streamlit application. Now I'm going to show you how you can load your model. So the model we have already saved here. Let me just show you the model here. We have already saved our model, and the name of the model is here BERT base uncaged sentiment model. So this is the name, and this particular name we are going to load using the pipeline. So the pipeline import have been already done in app.py. So this whole thing I'm just going to copy from here, and then I'm going to paste it here. Right now you see here classifier is equal to pipeline and then text classification, and the model name is here. You need to make sure that you provide a correct path for your model name. Currently I have my app.py and this particular notebook in the same directory. That is why I'm able to use this model properly here. All right, so now you have your classifier here. Thereafter, we need to pass some text data. Here you see there we passed our text data as the list here, and then we got the output as the list here. So we can do either by passing our data as the list, or we can pass data as a single string variable as well. So whatever you prefer, you can do that thing here. So this text data, we are going to read it from our Streamlit application text input or text area. All right. So for that, what I do here, I'm going to write here text is equal to st dot text area. Thereafter, I write here enter some text. Now thereafter, you come here and then you just write here rerun. All right, it is going to rerun this. Thereafter, you will see here you have got here a space where you can enter your text data. Then the label of this is enter some text here. I'm just going to say here enter your tweet here. All right. Thereafter, you come back again here. Then you can click on here always rerun. So with this you should be able to see here enter your tweet here. Now I clicked here always rerun. That means if we make any change there, that change will automatically reflect here. From the next time I don't need to refresh my page. I have got the text data. Now I need to provide their button. So to provide the button, I write here if st dot button, and then I write here predict. Thereafter, I write here result is equal to classifier. So this is my pipeline classifier. In this classifier, I'm going to pass my text data. Thereafter, I just need to write here st dot write and then result. If you want a very detailed tutorial on the Streamlit, so I have already shared here my playlist. So from here you can watch all the details about the Streamlit. If you are already aware with the Streamlit, then this should be fine to you. So you come here, thereafter now you see you have got here predict. Let's go ahead and enter some text data here. I write here I love you, let's say, then click on here predict. So after that you should be able to see your prediction. It says that the label is here love and the score is this much. Then let's say I write here I hate you, then it says that label is anger here and score is 68%. And similarly you can provide here any other twitch data whatever you want. Accordingly you will be getting here output. So this is all about in the Streamlit application development. That is how you can train your model, you can store your model. Thereafter you can give the path of your model with the pipeline in the transformer. Then you can use the Streamlit to host your application. There is another course where I have shown how you can put your model into the production. So that course you can also take from my Udemy page. If you like this video, please go to my that course is available at my Udemy page. You can go there and register into that course. I hope that you had enjoyed this section. So this is all about in this section. Let's go ahead and continue with the next lesson.